Okay, welcome to Organic Chemistry 2, where we now discuss aromaticity. If you're using the 4th edition of the book, this is chapter 13. If you're using the 5th edition of the book, this is chapter 14. So when we think about aromatic compounds and aromaticity, one compound comes to mind right away, and that's benzene. So we're going to take a little bit of time to explore benzene. And we'll begin by looking at its structure and talk about resonance in benzene. Benzene is the prototypical aromatic compound. It's a 6-membered ring in which there are alternating double and single bonds, and as per our recent discussions, this means that the molecule is conjugated. By conjugation, what we're talking about is the fact that every single one of the carbon atoms around the ring is sp2 hybridized, and therefore every single carbon around the ring has an atomic 2p orbital associated with it. So if I were to redraw benzene in a slightly different way, what I've essentially done is I've just taken this benzene molecule and turned it on its side. So some of the atoms are coming out at you, some of them are going away back behind the plane of the paper. The advantage of drawing the molecule this way is that suddenly I can see the p orbitals that are making up all of these pi bonds. In this drawing over here, those p orbitals are coming in and out of the plane of the paper, but now that I've turned it on its side, the p orbitals are in the plane of the paper, and they're a lot easier to see. So that's the side view of benzene where we see those p orbitals. Every single one of these p orbitals would have an electron in it. And we quickly realize that it's somewhat arbitrary as to where we show formation of double bonds. Any two adjacent p orbitals could have some pi bond character between them. And in fact, we can draw a resonance form for benzene now drawn this traditional way here, where we take these pi electrons and kick them there, and those over there, and those over there, and we have a new 6-membered ring. And wherever we had single bonds before, like here, here, and here, we now have double bonds. And wherever we had double bonds before, we now have single bonds. And so you realize quickly that it's truly arbitrary as to where you show those double bonds existing. This is a completely conjugated pi system, completely conjugated all the way around the ring. We need both of these resonance forms to really understand the structure of benzene. And the structure is one in which none of the bonds is truly a single bond and none of them is truly a double bond. All of the bonds are somewhere in between double and single. So that makes benzene an unusual molecule, different from others we've seen. The fact that it's fully conjugated is illustrated by this picture, where we see a continuous array of atomic 2p orbitals all the way around the ring. So when you look at this picture, you realize that there's just overlap between all of these p orbitals on top and likewise on the bottom as well. And for that reason, it's customary to draw benzene like this. This circle has a very specific meaning. It means that we have a completely conjugated pi system all the way around the ring, and the circle kind of represents the pi electron current. When you look at benzene, you know automatically that it must have an atomic 2p orbital at every carbon atom. That's what the circle means. And since it's neutral, we know that every single one of those atomic 2p orbitals must have just one electron in them. None of them are empty. None of them have 2 electrons in them. They all must have 1 electron, otherwise this molecule wouldn't be neutral. And when you think about that, you realize, well, these are just alternative ways to draw the molecule. Whether you show the pi bonds here, here, and here, or here, here, and here, or just show the circle, it all means exactly the same thing. So get used to these different drawings of benzene, and as it will turn out, other aromatic structures. It's a really important part of their story. But really, aromaticity is all about the pi system. The pi system is basically the collection of atomic 2p orbitals which go to form these pi bonds on benzene. We need to understand this pi system a little bit better. And so we need to talk about the pi molecular orbitals. MO here stands for molecular orbital. What is the molecular orbital picture or molecular orbital description of this molecule? And we can start by asking some simple questions like, how many pi molecular orbitals are there in benzene? And then we're going to see that we can actually figure out very quickly how those pi molecular orbitals are spaced energetically using Frost's circle. And we'll talk more about that in just a moment. But first, how many pi molecular orbitals are there? Well, you might remember from Organic Chemistry 1, when we first started talking about molecular orbitals and the relationship between atomic orbitals and molecular orbitals, that we had a very simple rule. If you're trying to figure out how many molecular orbitals you should be considering, all you really need to know is how many atomic orbitals are there which make up the molecular orbitals. Or in other words, the number of atomic orbitals in is always going to be equal to the number of molecular orbitals out. Molecular orbitals are prepared by combining atomic orbitals. So if you count up the total number of atomic orbitals, you can very quickly determine how many molecular orbitals you should be considering. Now we're talking about pi molecular orbitals here. And we know that a pi bond is made up of overlapping 2p orbitals on adjacent carbon atoms. So what we really need to count up in order to determine the total number of pi molecular orbitals we should be considering is simply the total number of atomic 2p orbitals. Each of these is a 2p orbital. So if I had a simple system like this, a molecule with one pi bond, and I'd like to know how many pi molecular orbitals are needed to describe it, that's simple. This pi bond is made up of two atomic 2p orbitals. Number of atomic orbitals in is 2, and therefore the number of molecular orbitals out must be 2. You might remember back in Organic Chemistry 1, we actually did an exercise like this. We had a couple of atomic 2p orbitals which we considered separately. So these are two different, distinct atomic 2p orbitals. They each have one electron, which we could show in a couple of different ways, either by putting an electron in the p orbital or by showing a spin up, and this one will be spin down so that they're spin paired. We know that these p orbitals mathematically are described in this way, where the two lobes of the p orbital have different shadings. One is shaded and one is unshaded. And we know that it's possible to combine these two atomic 2p orbitals in two different ways. In one way, we create a pi molecular orbital of lower energy. And this is the case where we allow these two atomic 2p orbitals to simply add together. And when they add together, we see that there are bonding interactions. You see these regions up here where there's both lobes are unshaded, or these regions down here where both lobes are shaded. Those correspond to bonding interactions, both top and bottom. However, it's also possible to take this p orbital here on the left and to subtract this atomic 2p orbital on the right. And when we subtract it, mathematically, we simply change the shading. So now, wherever it was unshaded, it's shaded, and wherever it was shaded, it's unshaded. And if I look across now, I see that this is actually a set of anti-bonding interactions between unshaded and shaded and unshaded. In other words, there's a node there. A new node has developed. So here we had 0 new nodes, and here we have 1 new node. A node is a site of zero electron density, and it means that there's not going to be any electron sharing between these two p orbitals, but these two down here, they only have bonding interactions. No anti-bonding interactions, no new nodes. I could redraw this pi molecular orbital in a way that shows that there's actually bonding going on, that there's sharing of electron density. So that would be another picture describing that situation up there. Well, this particular molecular orbital, which we'll call pi, sits at lower energy than either of the atomic 2p orbitals that made it, that were used to construct it. However, this particular molecular orbital, which we'll call pi star, the star indicating that it's an anti-bonding molecular orbital because it has more anti-bonding interactions than bonding interactions, it sits at higher energy. We need two atomic p orbitals to make a pi bond, two atomic orbitals in, two pi molecular orbitals out. We actually need two pi molecular orbitals to describe that pi bond. One is bonding, one is anti-bonding. Where do the electrons go? Well, they're going to feed down here into the pi molecular orbital that is of lower energy, that is pi, not pi star. One electron are now both sitting down here at lower energy than where they started. So that's a little bit of a review of some things that we did back in Organic Chemistry 1 when we talked about the construction of molecular orbitals, in this case pi molecular orbitals. Well, what about benzene? Back to benzene. Benzene's got all of these atomic 2p orbitals associated with it. How many pi molecular orbitals are going to be required to describe benzene? Well, since there's 6 atomic 2p orbitals, which by the way we could have quickly figured out from this drawing right here. Again, the circle means it's completely conjugated, which means every single one of those carbon atoms around the ring has an atomic 2p orbital associated with it. And there's 6. So this drawing really gives us the same information as that drawing as long as we know what that circle means. And likewise, these drawings do as well, because we know that these are alkenes, these are pi bonds, and so every one of these carbons must also have an atomic 2p orbital associated with it. Regardless of which cartoon drawing of benzene you focus on, the story is the same. There are 6 atomic 2p orbitals describing the pi system of benzene. 6 atomic orbitals in equals 6 pi molecular orbitals out. So we need 6 pi molecular orbitals to describe the pi system of benzene. 6 pi molecular orbitals. That's a lot of pi molecular orbitals, and the question is, how would we space them on an energy axis? Where would they be located? Down here we had a pi and a pi star, the pi at lower energy, the pi star at higher energy. How are we going to get these 6 pi molecular orbitals on an energy axis? Well, the truth of the matter is we can locate them on this energy axis pretty easily using Frost's circle. Frost's circle is basically a simple method or device that we utilize in order to answer this very question, in order to figure out exactly where these pi molecular orbitals are located, energetically speaking, relative to each other. In order to use Frost's circle, we realize that benzene is nothing more than a regular polygon. In this case, it's a regular hexagon. And we're simply going to inscribe this hexagon inside of a circle, but we're going to do it in a particular way. We have to ensure that one of the vertices, doesn't matter which one you pick, one of the vertices has to be at the lowest possible point on that circle. And as soon as you do that, and you go ahead and you inscribe it in the circle, you get something like this. Your drawing might look a little better than mine. And I'm going to put a little dot along that circle everywhere that a vertice touches the circle. If you've done this accurately, every point, or at every point on the circle where a vertice of the regular hexagon touches, that represents an energy level of one of the pi molecular orbitals. So notice that there's 1 at the very bottom, then there's 2 up above, These two are degenerate with respect to each other, which means they're of equal energy. And then there's two more above that, which are degenerate. And then finally there's one all the way up at the top, which is unique. So this would be a very crude but fairly accurate picture of how the 6 pi molecular orbitals of benzene would be placed along an energy axis. Well, all that's left is to figure out where did the pi electrons go. You have to know how many pi electrons you're dealing with, and once again, if we go back to these pictures, it should be pretty obvious. In this picture of benzene, there's 2 pi electrons, 2 more there, 2 more there, there's 6 pi electrons. But actually, this picture told me the same thing. This picture told me that every carbon had an atomic 2p orbital associated with it, fully conjugated. That's what fully conjugated means. And since it's neutral, there's no charge indicated, each of those p orbitals must have 1 electron in them, and that's a total of 6 electrons in 6 p orbitals, which are making up the pi system. So there must be 6 pi electrons. So there's 6 pi electrons. Where do I place them? Well, we always do that in the same way. Place the first 2 in the lowest energy molecular orbital. The third and the fourth would go into those degenerate orbitals, and then we go back and backfill until we've used all 6. And so this could be pi 1, pi 2, pi 3, pi 4, pi 5, and pi 6. And it's going to turn out that in benzene, pi 1, pi 2, and pi 3 are bonding molecular orbitals, whereas pi 4, pi 5, and pi 6 are all anti-bonding molecular orbitals, so we'll call them pi stars. Now we'd need to look at the details of those pi molecular orbitals in order to figure that out. Don't worry about that right now. Frost's circle just tells us how these pi molecular orbitals are spaced energetically with respect to each other, and it's very easy to fill in where the electrons would go. If you'd like, you can show the spin of the electrons, but it's kind of just assumed that those are going to be spin paired. So that is my 6 pi molecular orbitals associated with benzene drawn along an energy axis. So we've talked a lot about benzene here. We know something more about its structure and resonance, and something more about its pi system, and even something more about the 6 pi molecular orbitals that are required to describe it, and we use Frost's circle to help us out there. That's all very good. But none of that actually gets to the question of the word, aromatic or aromaticity. What is it exactly that makes a molecule aromatic? Why is benzene aromatic? Is it because it has pi molecular orbitals? Is it because it's fully conjugated? Is it because it's a ring? What is it about benzene that makes it aromatic? Benzene was probably first called aromatic because of its odor. And if you've ever smelled benzene or other aromatic compounds, they do have a distinct odor. It's not particularly pleasant and it's not particularly unpleasant. It's just distinct. Aromatic compounds have a distinct odor. And it's fairly certain, if we went far enough back in the chemistry literature, that there'd be reference to the odor of organic aromatic structures or aromatic compounds. And so that might have been the first definition of aromaticity. But over time, organic chemists came to realize that aromaticity means much more than how these compounds smell. It also means and refers to their reactivity. And in particular, aromatic compounds are not nearly as reactive as, for example, alkenes are. So let me show you an example. If I were to take this 6-membered ring, which has a pi bond in it, this is cyclohexene, I know from all of our recent studies that it undergoes a lot of different chemistries. I'm just going to arbitrarily pick a halogenation reaction. This is from Organic Chemistry 1. It's a halogenation of an alkene, and I know that it proceeds through formation of a bromonium ion and ultimately leads to an anti-vicinal dibromide. In this case, I'd produce a racemic mixture. This is one of the enantiomers. It's reactive. Alkenes are reactive with bromine and with lots of other reagents. In fact, you can use this particular reaction as a test for alkenes. If you had a test tube, let's say, with some compound in it and you weren't quite sure what that compound was, but you thought it might be an alkene, You could take a drop of bromine, which is an orange colored solution, drop it in there, and if the orange color went away, then that would mean that the bromine reacted with the molecule, and it could quite possibly be an alkene. So that would be a chemical test for alkenes. If you tried that same experiment, but instead of using cyclohexene, you used benzene, you'd see that there's no reaction. Benzene, despite the fact that it has 3 pi bonds, doesn't react with bromine. Cyclohexene reacts quickly. This reaction would be over at room temperature within a minute. This one doesn't react at all. Well, that sort of observation that aromatic compounds are less reactive than alkenes, it's been known for many, many years. And so there's no doubt that at some point the word aromatic or aromaticity was related to the lack of reactivity that these compounds showed. As time went on, people began to understand that the lack of reactivity is related to their energy. Aromatic compounds are sitting at lower energy than alkenes and other structures, and that's why they're less reactive. They're already sitting at low energy. There's less driving force, less energetic driving force for them to react. And it turned out that understanding led people to wonder, and in particular I'm talking now about people who we would refer to as theoreticians, people who study the theory of chemistry. It led them to wonder, what is it specifically about benzene, or are there some characteristics of benzene which we could point to, which would lead us to understand exactly why it has reduced reactivity, why it has low energy. Well, it was indeed possible to study benzene and other aromatic compounds using various levels of theory, and we're going to spend some time now talking about one of those theories, which has turned out to be really important. And I refer to work done by a theoretician named Huckel. Huckel developed his rules for aromaticity, and these rules, developed many years ago, are so useful and so helpful we continue to use them today to quickly identify aromatic structures. Now, as I said, Huckel was a theoretician, so his theory is based on mathematics, and there are ways in which one can study organic compounds and pi systems in particular using mathematics. We're talking about the math associated with quantum mechanics. Quantum mechanics describes molecules and electrons in molecules. It's very different than Newtonian mechanics. Those are the sort of mechanics you might have used in physics class, like Physics 1, where you try to describe how a baseball or some other object that's macroscopic, that's in our lives, moves, maybe through the air with gravity acting on it. That's called Newtonian mechanics. But molecules with these tiny little electrons, they behave very differently than baseballs. And we need quantum mechanics to describe them. Now, Huckel was a theoretician, and he knew this, and he studied these aromatic compounds. And what we're going to look at here is just the output of his work. We're not going to delve into the high-level quantum mechanical calculations. We're just going to look at the output. Huckel's rules, Huckel's mathematical treatment tell us that aromatic compounds must be cyclic. So, kind of like benzene. Benzene's in a ring. They must be fully conjugated. Benzene is fully conjugated. They must be flat or planar. Now that's an interesting one. The reason that they must be flat is that those p orbitals, which are all in conjugation, they need to be parallel to one another. If I have a couple of p orbitals which are sitting next to each other and they're parallel to one another, then they might be oriented like this. As soon as I start to twist one out of parallel, and in this case I've twisted it all the way to orthogonal, they're now 90 degrees with respect to each other, that happens in a molecule when the molecule loses planarity. So if I were to take a benzene ring and somehow twist it and make it something other than planar, I would see that those p orbitals would twist, And once they're orthogonal, there's no more interaction between them. Those orthogonal p orbitals may as well be a million miles apart. They don't realize the other one even exists next door. They don't talk, they don't communicate, and we talked about this when we discussed conjugation. So Huckel figured this out, and he realized it wasn't enough to be cyclic and it wasn't enough to be fully conjugated, but fully conjugated implies there's an atomic 2p orbital at every carbon around this ring, this cyclic ring, but the structure must be flat or planar, or at least close to flat or close to planar, so that those p orbitals can communicate effectively with one another. So that's all good. And then the last piece is the following. Huckel also figured out that the total number of pi electrons in an aromatic pi system, in a molecule like benzene that shows particular stability, unusual stability, which we refer to now as an aromatic structure, must have a certain number of pi electrons associated with it. Any old number of pi electrons is not going to work. It has to be a specific number. In fact, there's a simple algebraic expression, 4n plus 2, which describes the number of pi electrons that these aromatic molecules must have. This is just an algebraic expression. N is a variable, a mathematical variable, just like you've used in algebra class before, and it can be equal to 0 or a positive whole integer. N has nothing to do with the structure of the molecule. It has nothing to do with anything structurally related to the molecule, like, for example, the number of p orbitals or anything like that. N is nothing more than a variable which is confined to these values, 0 or some positive whole integer. This simple algebraic expression, 4n plus 2, is terribly useful, because if a molecule obeys these first three rules and has 4n plus 2 pi electrons, according to Huckel, it will be aromatic. Well, let's look at benzene. We know benzene's aromatic. There it is. We could draw it that way. We could draw it this way. We've discussed that these mean exactly the same thing. Well, let's look at the rules. Rule number 1, the molecule must be cyclic. This is cyclic. It's in a ring. Must be fully conjugated. That's what the circle means. Every carbon atom around the ring is sp2 hybridized, which means everyone has an atomic 2p orbital. That is fully conjugated. Every single carbon around the ring has got a 2p orbital. Must be flat or planar. It is. I've drawn it in the plane of the paper, and it would be completely flat. All the carbon atoms would be in the plane. And if it's aromatic, it must have 4n plus 2 pi electrons. Well, how many pi electrons does benzene have? Benzene has 2, 4, 6 pi electrons. This drawing also tells me 6 electrons because there's 6 carbons around the ring. Every one has an atomic 2p orbital. It's neutral, so every one must have an electron in it. That adds up to 6. Whether you calculate it from this drawing or this drawing, 6 pi electrons. That is, in fact, a 4n plus 2 number, because n can equal 0 or 1 or 2 or 3, etc. When n equals 1, 4n is 4 plus 2 is 6. 6 is a 4n plus 2 number. It's like a magic number. If you have a 4n plus 2 number associated with your molecule, it can be aromatic. Here's a simple table where we look at 4n plus 2 pi electrons. If n equals 0, 4n is 0 plus 2, then the number of pi electrons would be 2, and that's a magic number. 2 pi electrons with the other 3 rules satisfied, cyclic, fully conjugated, flat, or planar. That is going to be an aromatic structure. If n equals 1, 4n plus 2 becomes 6. If n equals 2, 4n plus 2 becomes 10. If n equals 3, 4n plus 2 becomes 14. These are the magic aromatic numbers, the number of pi electrons that must be associated with the molecules that otherwise satisfy these first 3 rules. And if you have all 4 rules obeyed, according to Huckel, the molecule will be aromatic, which means it will be, just like benzene, showing unusual stability. Well, it turns out this theory is quite old, and so people have had a lot of time to test it. And ultimately, you judge the importance of any theory by its ability to stand the test of time, to be tested over and over again to see if, in fact, it holds up. And it turns out that Huckel's rules for aromaticity do hold up. There are no known exceptions. Molecules that obey these rules are indeed aromatic. So let's look at some examples. I got a whole bunch of drawings here of molecules that may or may not be aromatic. We need to go ahead and examine them all. Let's start with this one. This is a cyclobutadiene. Looks a lot like benzene, except it's only 4 carbons instead of 6. And this drawing, as with benzene, means exactly the same thing. It means all 4 carbons are sp2 hybridized. All 4 have an atomic 2p orbital associated with them. In other words, it's fully conjugated. So this drawing and this drawing are really one and the same, just like they were with benzene. Now let's think carefully about this structure. Is it cyclic? Yes. It's definitely cyclic. Is it fully conjugated? Yes. Every carbon is sp2 hybridized, must have an atomic 2p orbital. Is it flat or planar? Well, as I've drawn it, it is flat. Does it have 4n plus 2 pi electrons? Well, let's count up the pi electrons. 2, 4. If I thought about this drawing of this same cyclobutadiene, telling me it's fully conjugated, and notice there's no charges shown, so every p orbital around this ring must have 1 electron. That adds up to 4 as well. There are 4 pi electrons in this molecule. Is that a 4n plus 2 number? Well, it turns out no, it's not. It's not a 4n plus 2 number. 4n plus 2 numbers are 2, 6, 10, 14, etc. Not 4. So this molecule is not aromatic. It obeys the first 3 rules. It's cyclic, fully conjugated, and flat, but not the last rule. Let's look at Frost's circle. Remember that? Frost's circle says that if you have a regular polygon, a molecule that is a regular polygon, in this case a square, you can inscribe it in a circle, but you have to do it in such a way that one of the vertices is at the lowest possible point. And when we do that, oops, we're going to get something that looks like this. I've inscribed my square inside the circle with one vertice at the lowest possible point on that circle. Where those vertices touch the circle represent the energy levels of the corresponding pi molecular orbitals. This molecule should have 4 pi molecular orbitals because 4 atomic 2p orbitals are part of it. 4 atomic 2p orbitals in, 4 pi molecular orbitals out, and those 4 pi molecular orbitals will be distributed about each other, energetically speaking, as is shown here according to Frost's circle. Well, let's fill in the pi electrons. There's a total of 4 pi electrons to fill in. The first 2 would go down there, the third and the fourth would go there, and now we're out of electrons. And we notice something very peculiar. This molecule has 2 unpaired electrons sitting in these pi molecular orbitals. We could call this pi 1, pi 2, pi 3, and pi 4. 2 unpaired electrons, one in pi 2 and one in pi 3, these degenerate pi molecular orbitals. This molecule behaves like it's a radical. In fact, it's more than just a radical, it's a diradical. Well, we just finished studying the chemistry of free radicals, and we know that free radicals are reactive intermediates. Organic free radicals, we put brackets around them because they have short lifetimes. They're highly reactive species. This is a diradical, a molecule that has 2 radicals on it. This molecule is not only not aromatic, but it looks like it should be really unstable. According to this description, it would be a diradical, very high in energy. In fact, it's true. This simple molecule, innocent as it may appear, is incredibly unstable. Whereas benzene shows unusual stability, this cyclobutadiene shows unusual instability. In fact, it's never been isolated at room temperature. It's only been isolated at very, very low temperatures, close to absolute 0. But as soon as you start to warm it up, it does some chemistry and turns itself into something else. So Huckel's rules for aromaticity are spot on. They tell us exactly when a molecule will be aromatic, and it turns out, if we kind of read a little bit more into it, we can not only tell when molecules are aromatic, but we can tell when molecules are so-called anti-aromatic, which is what butadiene is. Anti-aromatic molecules obey Huckel's first three rules, but have 4n rather than 4n plus 2 pi electrons. Just like this butadiene, it has 4n pi electrons. The total number of electrons is 4. That is a 4n number where n equals 1, not a 4n plus 2 number. So 4n is the number that we assign to molecules that are anti-aromatic. They show unusual instability, unusually unstable. Kind of just the opposite of aromatic. Isn't that interesting? Two molecules which look so much alike. We're talking about butadiene and benzene. They look a lot alike. One of them, benzene, is unusually stable and sits at very low energy. One of them, cyclobutadiene, is unusually unstable, sits at very high energy. In fact, it's a diradical. Amazing. And we can get all of this from some simple rules. Let's go back now and look at some more structures. As I said, theory becomes most important when it stands the test of time. We've studied this one. It does not obey Huckel's rules for aromaticity, but as we realize now, it is actually anti-aromatic. What about this molecule? Wow, this one looks like a mess. It's got a three-membered ring. We know there's a lot of angle strain associated with three-membered rings. We know there's torsional strain associated with these three-membered rings because of eclipsing interactions. And look, I've made it worse. I've turned it into a carbocation. We know carbocations are high-energy species, unusually unstable in their own right. Organic compounds generally don't like to be present or exist as carbocations. We would call this a cyclopropenyl cation. Let's take a careful look at this cyclopropenyl cation, which I will redraw here. Notice that I can draw it this way. This circle means it's fully conjugated, but there's a positive charge, which means if I were to draw all of the p orbitals associated with this fully conjugated system, two of them would have electrons in them and the other would be empty, and hence that's where the positive charge comes from. And we know it's conjugated, so it's somewhat irrelevant as to where the electrons are shown. You could show the two electrons here, you could show them there, you could show them there, but there'll always be two p orbitals with one electron each, and one p orbital that's empty. That's what that picture tells us, and that's also what this picture tells us. We could show a resonance form here. Whoops, sorry about that. We could show a resonance form where we move these pi electrons over here, and now the positive charge migrates there. And that was such a sloppy drawing. Let me try that again. I'll draw them all facing this same direction. So I just move these pi electrons over here, and now my positive charge moves there. And what if I move these pi electrons over there? Now my positive charge moves to that carbon. So what I see is that all three of these resonance forms are important. They basically tell the story that every single one of the carbon atoms around this three-membered ring share in the positive charge density. And that's pretty much what this circle with the positive charge in the middle also implies. So it looks like a train wreck. It looks like a terrible molecule. Let's figure out whether or not it is aromatic according to Huckel's rules for aromaticity. Well, is it cyclic? Yeah, okay, it's cyclic. No big deal, it's a three-membered ring. Is it fully conjugated? It is. Every carbon atom around the ring has an atomic 2p orbital associated with it. That's our definition of fully conjugated. Is it flat? It actually must be flat. It's impossible for a three-membered ring not to be flat. We define a plane by any 3 points. So if you pulled one of these points, one of these carbon atoms out of the plane, you just define a new plane. So a three-membered ring must, by definition, be flat or planar. So it fulfills the first 3, but what about this one? 4n plus 2 pi electrons. How many pi electrons are in this? Well, looking at any of these resonance forms, there's only 2 pi electrons there. That's also implied in this drawing. The circle means that every carbon has an atomic 2p orbital associated with it. If it were neutral, there would be 3 pi electrons, but since there's a positive charge, one of those p orbitals is missing an electron, so there's only 2 pi electrons. So anyway you cut it, there's only 2 pi electrons here. We go back to our table. 2 pi electrons is an aromatic number. 4n plus 2 equals 2 when n equals 0. 4 times 0 is 0 plus 2 is 2. That's an aromatic number. According to Huckel's rules for aromaticity, this compound, this outrageous compound, three-membered ring with a cation, is aromatic and should show unusual stability. Well, this molecule is actually one of the greatest tests for Huckel's rules for aromaticity because it looks like it's a total train wreck. It has everything going against it, but it turns out it shows unusual stability. It is indeed aromatic. This molecule can only be seen close to absolute zero. This one shows unusual stability. Go figure. The only way you can make sense of this is if you realize that this one's aromatic and that one's anti-aromatic. Let's go to another one. This is a cyclopentadienyl anion. Cyclopentadienyl anion. Let's take a careful look at it. Drawn this way, the circle means every carbon is sp2, which means there's a p orbital associated with every one. There's 5 carbons, that's 5 p orbitals. The negative charge means one of those p orbitals has an extra electron such that the molecule as a whole has a negative charge. So 5 p orbitals with 1 electron, but then there's an extra electron, means it has 6 pi electrons. That's the same number of pi electrons as benzene. As long as all the other rules are satisfied, this molecule will actually be aromatic. Is it cyclic? Yes. Is it fully conjugated? Yes, that's what the circle means. Is it flat or planar? Yes. And does it have 4n plus 2 pi electrons? Yes. When n equals 1, 4n plus 2 equals 6. It has 6 pi electrons. This molecule is also aromatic. What about Frost's circle? If I inscribe this regular pentagon into a circle, it would look something like that. Wherever the vertices touch the circle, that defines the energy value of the 5 pi molecular orbitals associated with this molecule. In other words, one would be sitting at lowest energy, there would be 2 degenerate orbitals up above, and then 2 more higher up above. We could call this pi 1, pi 2, pi 3, pi 4, and pi 5. I know there's a total of 6 pi electrons in this molecule, so let's fill them in. The first 2 would go down there. The third and the fourth would go there and there, but then the fifth and the sixth would completely fill those pi molecular orbitals, such that there were no unpaired electrons, as we had with butadiene. This molecule has all of its low-lying pi molecular orbitals filled. That's going to turn out to be the characteristic of one of the characteristics of an aromatic structure. This molecule is indeed aromatic, and in fact the cyclopentadienyl anion, this molecule right here, is quite stable. Carbon doesn't generally like to exist as an anion, but this one is quite stable because it's aromatic. So far, Huckel's rules for aromaticity are working out time and time again. They're helping us to explain observations that we see. This molecule and this molecule, we might not have expected them to be stable, but it turns out they are. And that's because they're both aromatic. That molecule looks better than that one for sure, and probably better than that one, is unusually unstable and anti-aromatic. And on we go. All of these drawings here represent molecules that are cyclic, fully conjugated, and flat, at least as drawn, they're flat. So you should assume that they're flat if they're drawn flat. This one is a 7-membered ring. Notice that one of the p orbitals doesn't have an electron in it, hence the positive charge. That could be drawn this way as well. If you count up the total number of pi electrons, it's 6, 2, 4, 6. This is also an aromatic structure. Another aromatic cation. This particular cation, this aromatic cation inside of a 7-membered ring, is known as a tropylium cation. That's a generic or historic name, trivial name, that it's not IUPAC related, but most people would refer to this structure as a tropylium ion. Look at this structure. It looks like a stop sign. It's an 8-membered ring, and it's fully conjugated. It looks a whole lot better than that one. There's no positive charge in it. But if you count up the total number of pi electrons, 2, 4, 6, 8, it's got 8 pi electrons. That's not a 4n plus 2 number. You won't find 8 on this table. It's actually a 4n number. 4n when n equals 2. This molecule is unusually unstable. It is anti-aromatic. Crazy. Well, let's see what's going on here. Let's look at these two structures using Frost's circle. So we start with the tropylium cation. And we're going to inscribe this 7-membered ring inside of a circle. This is not so easy to do. But if you do it reasonably accurately, ensuring that one of the vertices is at the lowest possible point of the circle, you'll come up with a drawing that looks like this. Energetically, the points on the circle where these vertices touch correspond to energy levels of the 7 pi molecular orbitals. Why 7? Because there's 7 atoms around there. It's fully conjugated. Every one of those carbon atoms has a 2p orbital in them. So in this pi system, there's 7 2p orbitals. Number of atomic orbitals in equals number of pi molecular orbitals out. This is 1, 2, 3, 4, 5, 6, 7. You see 1 at the bottom, 2 degenerate orbitals above, 2 more degenerate orbitals above that, and finally 2 more above that. We have a total of 6 pi electrons. The first 2 will go down there, the 3rd and the 4th, the 5th and the 6th, and lo and behold, just like with benzene, just like with the other aromatic compounds we've seen, the low-lying pi molecular orbitals are completely filled. Let's contrast that with this cyclooctatetraene. Now it's getting harder and harder to draw Frost circles here, but we'll give it a shot. Difficult to do because one of the vertices has to be at the lowest point of the circle, but if you do it, you realize that the spacing of the 8 pi molecular orbitals would be 1 at the bottom, 2 degenerate above it, that's those 2, 2 more degenerate above it, that's those 2, 2 more above it, that's those 2, and then finally 1 at the top, that's that one. And we've got 8 pi electrons to place in these 8 pi molecular orbitals. 1, 2, 3, 4, 5, 6, 7, 8. It's another diradical. This molecule, when it's planar, exists as an anti-aromatic structure. And as we're now seeing, all of the anti-aromatic structures have diradical character. Frost circle is turning out to be really useful to explain why it is that these anti-aromatic molecules with 4 n-pi electrons are so unstable. It's because they all have diradical character. Now, this brings us to an interesting point. So far, we've only run into 2 molecules that are anti-aromatic, this cyclobutadiene and this cyclooctatetraene. The cyclobutadiene, as I told you, is incredibly unstable and it can only be isolated near absolute zero. However, this molecule actually exists, and it's not terribly unstable, but there's more to the story. One of Huckel's rules, you may remember, it must be cyclic, it must be fully conjugated, and it must be flat. You see, when you're dealing with smaller ring systems like 3-membered ring and 4-membered ring, it almost automatically has to be flat. It does have to be flat if it's a 3-membered ring. As we described earlier, 3 points define a plane, so this must be flat. With a 4-carbon ring, like this cyclobutadiene, it's possible to pucker one of those atoms out of the plane and make it a little bit less than planar, but there's not much option there to pull a carbon atom very far out of the plane. It's a little bit restricted because of the geometry of the molecule. When you get up to a large structure like this, however, it is actually possible to adopt a non-planar conformation. And that's actually what cyclooctatetraene does. So if left to its own devices, this cyclooctatetraene will not sit in this planar conformation. This planar conformation is anti-aromatic.